just to acknowledge the people that annotate the images that we use to train our systems. And the person that annotates the images that we use is my mother. So I wanted to give you an update on her work. She's been annotating images since 2007. She is labeling images every single day. She enjoys this. So the last picture, this is taken yesterday. So she's probably not annotating images right now, but she will in a few hours. And all the data that she has annotated, we have made it available in a dataset that is called ADE20K. And these are images that are fully annotated, fully segmented with all of the objects, everything. So I'm going to be using that dataset a few times over the talk. So now you know where the data is coming from. So one of the goals of explainable AI is trying to build systems that can explain themselves, have a neural network that is capable of doing some interesting task, and you want to know how does it work? What is it doing internally? And the real question is, when is that an explainable system? When is that the explanations are actually useful? What do you want to do with them? So some of the things that make a system that explains itself useful is that, well, it should give you some predictable capabilities. You should be able to predict when it's going to fail, not just explain the failures, but actually be proactive and explain when it will fail and how. You also should be able then to change the network behavior, because if you know what it's doing and the system can explain itself, then you should be able to intervene and make changes into the system. And then you should be able to repurpose the representation, because if you really understand what it's doing, then you should be doing things other than the ones that the network was trained for. You should be able to do new things with it if you understand what the representation was. So you should be able to understand when it fails and make it fail on purpose. So there are a number of different approaches, and you will be hearing about them also during this workshop. There are visualization-based techniques. There are all kinds of different techniques. The ones that we are going to be using here are a family of descriptions that we use, that we call network dissection tools. Our goal is that the representations should be quantifiable and reproducible. That means that if you have a system and you run the explainable tool that you have, it should always give you the same answer. If you have always the same system, you should be able to compare systems. You should be able to quantify how good that explanation is, and so on. So visualizations sometimes don't have that. So one interesting thing that happens is that when you train a network, it feels like a black box, but the truth is that these visualization techniques that people have been using have shown that internally, there seems to be something that makes sense. The units, the neurons inside, seems to be solving auxiliary tasks that are relevant for the final task, and they seem to be kind of interpretable to some degree. So here is one example of a unit of an AlexNet network that was trained to do scene recognition, and these are the top images that most strongly activate that unit and the regions that activate that unit, and this seems to be a lamp detector. And there are no mistakes in these top segmentations. It's all detecting lamps. And this is a completely different task than what the network was trained for, it was trained to do scene recognition. It wasn't trained to do lamp detection. There were no annotations for lamps. It's just something that emerged inside. Here there is another unit in a ResNet network, also trained for place recognition. And this seems to be detecting pool tables. And it seems to be pretty good. There are some mistakes. Here there are some mistakes. There are green things surrounded by a square frame or something like that. It still seems to be strongly biased towards pool tables. Like there are some traffic signs here that are detected, but there are many traffic signs on this data set, and there are only a few that have produced false alarms here. So this seems to be kind of a pool table detector. So the goal of network dissection is to use this insight and try to explain what every single unit is doing. And the way that network dissection works is you take a bunch of images, you throw them to a network that has already been trained. And let's say that you're interested in understanding what a particular unit is doing. So the images that you introduce are images that have been annotated. Here we just, what my mother has been annotated over all these years. So we know every single thing in the image what it is. And then, you look at what are the images that most strongly activate a particular unit. This is a very classical technique used by many people. And then now, because we have segmentations, we can match what the output of this seems to be selective for with the elements in our dictionary, measure the agreement. You loop over all possible concepts that you have in your dictionary, and then you pick the one that explains the best the output of that unit. And if that's above some certain threshold, then you say, well, this unit seems to be doing this. And you can do the same thing with generative models. In this case, a generative model doesn't take as input an image, it outputs an image. But you can do the same thing. You can look at one unit, look at what are the regions that get activated for that unit, and generate the images. Look at the images that get generated when this unit was most strongly activated. And again, you can now run some semantic segmentation algorithm on the output images that are generated, and again, measure the agreement between what the unit seems to be selective for when those images got generated, what the concepts have been detected on that image, and loop over all possible concepts, all possible units in the network, and start doing this pairment matching. And then you get these interesting plots of the concepts that are found inside each layer in a neural network. So here on the left is a BGG net, and these are the different layers, and the histograms here is just the counts of how many objects and different concepts have been found for all the units in that layer. So you can see that near the input image, there are very few concepts. And as you get closer to the output, there are more and more concepts that are being detected. Makes a lot of sense. On the right is a generative model, which has a different behavior. Most of the concepts are found in the middle. Like if you're too close to the random vectors, there are no concepts. It's still just the latent space. It's all very global. There are concepts there, but it's very encoded in a very global way. If you are too close to the output, there are also no concepts because the resistive fields of the units are too small, and it's all about putting the right colors and the right edges and so on. It's in the middle where you start finding units that seem to be selective to objects. But there is a strong limitation here, and this is something that we wanted to work for a long time in trying to address the following problem. You have a network, and you look at some units, and they don't seem to be doing anything that you can put a name for. Here is a unit in an AlexNet, and these are some of the images that, so the images for which it was most strongly activated, this unit. And it doesn't look like any object. It looks to be something, some property of the visual, the visual stimuli, but it's not an object per se. Really what you would like to do is if you ask people, they will start writing things like, well, it seems to be detecting objects that are in pairs, or maybe the edge of two round things next to each other, or two objects that are the same next to each other. Now, there seems to be selecting maybe some symmetry. There is not a single object that you can put here. So you have a limited dictionary. This is not going to work very well. And here there are some other examples of human annotations. So if you ask people to annotate what they think a unit is doing, they do something very different than from what network dissection tools do, which just assign a single word. Now here is a unit that is selective to what it seems to be dog faces. So this is what people will say. This is faces of dogs with dark muzzles, or faces of canines, dog faces. Now these are just three different people annotating this unit. Here there is a different unit. This, what is this doing? Well, it seems to be detecting something like yellow, red, and orange objects. It's very fussy. And the problem also is that even human annotations are not perfect. They can be vague and also quite generic. So for instance, here, there is a unit that is selecting this type of patterns. And when you ask people to tell you what this unit is doing, they say, well, it's detecting some pattern fabric. Okay, that's great. And then you show them a different unit that detects a different pattern, and they also tell you, okay, a pattern fabric. This is not exactly what you want. You want something that really tells you the difference between these two units. No, you want something that starts explaining the type of texture that this unit seems to be selective for. So what we did was a new version that we call Milan. It's a new version of network dissection that what it will do is really trying to annotate the behavior of units using full language descriptions, just something like image captioning, but for units. You want to have a unit and you want to have a system that will automatically caption what that unit seems to be doing. And you want to have this with free language, open vocabulary, so that it can describe whatever the behavior of the unit is, just as a human would. Even better if possible. No? So the first thing that we had to do was to collect a data set of annotations for the behavior of the different units. So, we did it on Amazon Mechanical Turk. We show workers 15 images that were the top the top units, images that most strongly activated a particular unit with the regions where that unit was actually active. So these are the examples. So in this particular case, this unit seems to be detecting the sky. And then we just ask people to type a description of what was in common across all of these different images. And so this is one example. And then we loop over all units and a bunch of different networks and different tasks for which we train those networks. So we had a lot of data. Here there is some examples of annotations. Here is a unit that seems to be detecting windows, and people say car windows and dog eyes, because there is a dog on the bottom row. And people can be very precise on the annotations. Here there is another one. This is the output of a generative model. This unit seems to be drawing faces, kind of scary faces, but faces after all. And this is what people wrote. They had no idea this were generated faces or anything. So they just said, okay, distorted faces of people and pets. There is one dog face that appears in this case. Here there are some other examples. Sometimes the annotations are not great. Like for instance, here, the second subject say that this is detecting objects that start with the letter B, which I don't know what to do with that, no? But okay, why not? So we collected a lot of data. We have around 17,000 different units from 7 models. We have 3 people describing each one. So we have around a total of 50,000 descriptions that we make available for people to use. So now you can train your kind of unit annotator. So this data set is already available there. So then the model that we use is relatively simple. You can use your favorite image captioning system and just plug it here. You need to make a few changes so that it has to take as input not one image, but a set of images with a mask. And then you need to output the descriptions of that. So in our case, it's just a very simple system. You start with the top activated images. You pass them. In this case, we use a version of show and tell, which we modified so that it took as input set of images with masks. And then that goes into an LSTM that will output descriptions. So here we generate multiple descriptions, not just one. We generate a bunch of them. And the problem with this is that if you just do this, then generally the one that has the highest probability generally happens to be very generic. So another thing that we did was to train another LSTM with only the annotations of units to compute the probability of each description without conditioning on the image. And we wanted to find descriptions that were both descriptive of the image, but also not typical. So we wanted to create something that was more specific than the just most generic and typical description that you could have. So you can accomplish that by just subtracting these two probabilities, and then you get a new numbers, and at the end you get this types of building as a description that is not as common, but it's a little bit more descriptive of the content of the picture. So the details are not super important here, and you can find all the details on the paper. So what are the results? Then here is we run this in a bunch of data sets and networks, and you can train also with some networks and then test on different sets of networks, and we found that it generalizes very well. So here there are some results. Now, this is one unit that seems to be detecting legs. So humans will say legs of different animals, and our system says animal legs. Here is another unit that seems to be detecting like volcanoes. So human says erupting volcanoes, and Milan says volcanoes and eruptions. Another one here, seems to detect dog faces. The human will say dog faces and monkey face because there is one monkey here. It will take you a while to find it. And the top part of cupcakes. For some reason, this unit that really loves dogs, the most important image that has most strongly activated this unit was the first one that just has cupcakes. I don't know why. Anyway, Milan just says dog faces. Another unit here that is detecting like the top of buildings. So both humans and Milan say something very similar. There are units also, the nice thing about having this open world vocabulary annotations is that you can interpret the behavior of units that really don't do objects. They start doing things like edges and so on. So here there is one unit that seems to be doing something weird. So the human will say this is like fighting on flat lanes and surfaces. And Milan is just saying the top of boundary of horizontal objects. So these captioning systems can get quite interesting. And in fact, this shows a little bit the need of collecting the data set that we built, because many of these captions are very hard to use in popular data sets that exist nowadays, because they normally focus on objects and scenes and behaviors and actions. And here, we really needed something that was able to talk about low-level characteristics of images, like horizontal surfaces and so on. Here there is another example of another unit that seems to be detecting like the boundary of round things, and Milan says round edges on objects. Another unit here, this is like a strange unit that seems to be detecting these weird patterns, and there is nothing useful. Sometimes the annotations will make no sense. Like here, it says similar patterns. Like I don't think that that's very useful. And here there is another unit that it seems to be kind of chaotic, detecting all kinds of stuff. And the human will say animal bags and driver seats. And Milan says means of transportation. And sure, you can, probably be on top of one of these animals, but it just doesn't feel very safe. No, I don't think that's really what the unit is doing. So it's not perfect, far from it. And here there is another, really bad example where this unit seems to be detecting, I don't know, kind of yellow objects with lines. So, the human says yellow and green animals, food, instruments, and objects. No, not a very useful description. And Milan says noodle dishes. Okay, so this is the state of the art of what is happening right now. But the truth is, at the end, it kind of works fairly well for a number of different things. And we think that also scaling up the data set of annotations that we have probably will improve performances substantially. I mean, 50K annotations is a lot of annotations, but it's shy from the numbers that people are currently used to train like really big language models. But really, what I think is interesting about explanations is not really to explain what the system is doing and why it's doing it, is to perform interventions on the system. And that's what I want to focus on the last few minutes of the presentation, is what can you do beyond explanations? Like if you have a system that is capable of telling you what the system is doing, what can you do with it? So I think that there are a number of different things that you can do, and I want to flash just a few of them. So one of them, you can actually try to predict the network behavior, and in particular, vulnerabilities that the system will have. So here is an example of one of the networks trying to do ImageNet classification. And this is the last layer. We are focusing on the last layer. And we focus on units that seem to have selected as a description something that is very diverse. It has lots of different objects in the description. So we know that this unit is just strange. Like this, there is a unit here that detects animals, vehicles, and bases. Okay, so what can that unit be useful for? It's detecting so many different things. So one thing is that if this unit is actually not useful, this could be a vulnerability for the system. So we can check what are the categories for which this unit is connected to on the output. And then we can use that to create adversarial attacks. So for instance, here, one thing that we can do is we can take an image, for instance, the ones shown on the left, the container ship. This is an image that is correctly classified as a container ship, but we have seen that you can actually, if you insert a vehicle in one of these images, the class for amphibian will grow in a score. So we can just take an image that contains a military car here, because that's the type of images that it likes, this unit. You paste it on top of the image, just in a corner, and then you run the classification, and that unit just activates the wrong class, because this unit was kind of misbehaving. It just has this very diverse set of stimuli that activate it. And just by knowing that, you can create these adversarial attacks just by cropping and pasting objects inside and you can fool the behavior of the network. So this is kind of telling you that this analysis that is a little bit correlational. No, finding these captions is more correlational than causal. But you can actually make interventions and see that actually it predicts mistakes that the network makes. There are other things that you can do. For instance, when you analyze generative models, if you know what the units are doing, you can do all kinds of things. Like for instance, here is an image that is generated by a GAN. And now what you can do, if you know which units are responsible of drawing windows, you can just turn them off, and then windows should disappear. No? And that's exactly what happens. The windows go away. And interestingly, there is still a wall, and there seems to be a painting with some abstract art, which is what GANs like. But the nice thing is that here you are performing this intervention. You are not retraining the network or doing anything. You're just deactivating the units, and it seems to work fairly well. Or you can take an image like this one. You can look at the units. There was a set of units that were responsible of drawing grass, and you just activate them, and grass appears everywhere, and it kind of seems to make sense. It's like 1,000 years have passed since humanity disappeared, and you have grass all over the place. There is another, there is this interesting behavior that is, if you understand the representation, then maybe you can reprogram the network by hand. Instead of having to put data and train it to do something else, just go inside, you know what the units are doing, and just rewire the network and ask it to do something else. So here is one really cool thing that David Bao did, which is these are two images that are generated by a GAN. One has the window units deactivated, and the other one on the right has the units for windows activated. And one cool thing is that you can see that there is a reflection that appears on the countertop. And we are just activating the units that render windows. We are not doing anything about lighting, and yet there is this reflection that appears on the countertop. And the question then was, who is drawing that reflection? And can you change that? And the idea is that there are these contextual rules between objects that are also encoded on the weights, and you can find them and start manipulating them. And that's what David did. So what he did was to find in the generator a very simple edit that you could make so that you could change the behavior of the network and manipulate those contextual rules at will. So what he did was to identify the networks, the units that were responsible, the weights that were responsible of creating those connections between windows and reflections, and reversing them so that now reflections will appear when there were no windows, and there were no reflections when there will be windows on the image. And that's what he did. So now, after that very simple edit, now whenever there are windows on the image, it looks like there are no reflections anymore appearing on the counter. However, there are lots of reflections when there are no windows. So this is an example of a very simple manipulation that allows you to reprogram what the GAN is doing. And now it's doing something that is outside of the training set. So I think this looks pretty cool. And finally, another thing is that if you understand the representation, one of the cool things is that these representations seems to be quite powerful. They seem to have discovered objects, and these objects are kind of distributed among few units. It's not like a single unit is responsible of that object and no one else is. Generally, it's a collection of units responsible for one object, but it's pretty localized. And the fact that you have this very meaningful representation means that maybe you can use that for a lot of different things. So one of the tasks that we had, and this was in collaboration with Sanja Findler's group, was to use them to annotate images. So we want to replace my mother by a system that will be able to annotate lots and lots of images automatically. And the idea is that if you have a style GAN, for instance, that renders images that look very, very realistic, the idea is, can you interpret what is going on inside and connect it with the semantics of this image to create now images that are not just pixels, but also contain segmentations. So the idea is the following one. You train your style GAN to render, let's say, cars. And now you annotate a few cars. You don't need to annotate many, just a few cars that are generated by the GAN. And you can add parts, so you can have a very detailed segmentation. And now you train an image, semantic decoder from the internal representation that the GAN is building, so that you can actually label the image. You just train to the code, the segmentation that you want to from the internal representation of the GAN. And because we have seen that these GANs learn things that are very meaningful, the hope here is that you really don't need to annotate a lot of things, because basically the system, the only thing that needs to do is to locate which unit is segmenting is responsible for drawing a particular object, and that's going to give you a very fine segmentation. So you don't need a lot of data in order to do that. So it will just be labeling just very few images. And if it is few images, you can actually label a very dense annotation of an object. You can add lots and lots of parts, something that maybe will be unfeasible if you had to label a big data set. So here we have like more than around 20 parts for cars. And so, and these are now, once you train that, these are synthesized images where it's just not just the pixels, but also the annotations that get synthesized. This is another synthesized data set of faces. And now the idea is that once you generate a data set that is fully annotated, first, now you have access like an infinite size data set of fully segmented images, that, whatever your favorite image segmentation algorithm is, or object detection. And, and then the goal was, okay, can we scale this to ImageNet size? Because, I tried to convince my mother to annotate ImageNet, she refused. So, but what if she labeled just a couple of images per class? Can then we use that train GAN to generate ImageNet, but fully segmented ImageNet? And these are images generated with big GAN, trained with ImageNet. Images look quite good. Not all of the classes look good, but many look very good. And then she labeled a lot of images. So you take ImageNet, you train a style GAN, you take my mother, you train the segmentation, and then you have access to an infinite synthetic annotated ImageNet. And that will be presented on Friday. So you will have more details there about how it works. So thank you so much for your attention. And
we have a question on Zoom, but I want to wait if there are any questions in person.
Do you wanna?
Let me just try to also do this. Dipti, there are questions in person, so let's start with that.
Okay.
So people on Zoom are having issues hearing them speaking on that microphone.
Okay, I'll repeat the question.
Yeah, great.
Okay.
Thanks for the nice talk. So I was curious about the last part on the data set gap. So I mean, I guess that what's interesting about this is you almost have a perpetual motion machine, right? You label a few images and you get unlimited label data, and that's fantastic. So I was kind of curious as to but having said that, I'm sure there's lots of stuff that is naturally learned within a GAN. I was curious as to your thoughts as to, what's the value we can get out of this approach in terms of scaling up labeling, and what are the limitations?
Yeah, so basically the question is, for those in Zoom, if this dataset GAN is kind of a perpetual motion machine, and what are the limitations really? How much can you get out of this? Well, yeah. So there are several limitations. First, the GAN needs to work. You should be able to generate really good images. Otherwise, it's not going to work. And the GAN is going to have some difficulties in generating the whole space of possible images. So that's going to be also a limitation. If you annotate real images, you will have more diversity. The GAN can only reduce the diversity. However, I think that one of the nice things that I think that kind of enables that perpetual motion machine a little bit is the fact that now you can intervene on the GAN and actually do edits on the GAN to enlarge the diversity of what it generates beyond what it can be seen in the real world, for instance. So it's not a perpetual motion machine because that requires a human intervening on the GAN to create that, but it's another way of starting compensating for the lack of diversity of the GAN. So I think that this is like a very interesting approach. My guess is that this kind of, and in fact, it's happening already in the community. Unsupervised learning is kind of taking over. And I think that this is one example of something that I think will replace like traditional labeling.
So maybe just to confirm, thank you very much. That's really the answer. So maybe just to confirm, what you're saying is that actually maybe this could act as like the first step in almost.
Yeah. It will be, it will be. So for those on Zoom, so this will be like the first step in an iterative system where you have humans intervening in different stages, or annotating more images, or editing the GAN to generate different types of images.
Thank you.
Thanks for the talk. I'm just curious, what do you think are the biggest challenges in implementation when we go from image objects to actions and activities handling data, especially for activities that might involve change of the appearance of the objects, and if we want to, on the network, to have cutting apples in pieces, then we like how we should really approach those.
Okay, so I'll repeat one piece of the question. I couldn't catch everything, so I'm happy to talk later. But basically, I think that, the question was about what are the limitations when you extend this, for instance, to video and for action recognition and so on. So just one very short answer. I mean, the precondition here is that the GAN should be able to generate the images that you have in your data set. And with video, it's just challenging. People are starting to create some really cool GANs that generate video, but it's still kind of early. So there are not good generative models for video right now. So I think that's the only limitation, but once there will be, I think, I don't see any problem. I think that you should just be able to do the same things.
Okay, we still have questions from the audience.
Have you tried to machine learning to group samples that then you get in description?
That you can get one?
With metric learning, you causing the interface to try to form models to group samples that similar to each other, but then we need to understand which samples are similar. But if they get in the same description, you can create some kind of iterating process that causing the latest traffic from the model itself to group samples that get in the same description.
I'm not sure I understood the question, so I'm happy to talk afterwards. But I think that the question was around a little bit. Can you group, the generated images according to their features or whatever, and then maybe generate descriptions according to those. So I think that relates a little bit, maybe as I understand it, or maybe I'm just putting thoughts on your mind. Relates to active learning, and I think that there is an interesting thing to do here, where you just sample images that are going to be informative for annotation, and you can group the images that get generated so that you are really annotating a very diverse set of images. Because we are annotating very few images, we didn't really have enough opportunity for doing active learning. I mean, we are annotating just really a handful of images per class, so just that random selection is already very diverse. So I'm not sure that active learning here will make a big difference, but I think that if we were doing something bigger scale or something, maybe there will be use for it.
Okay, Dipti, this is it from the audience questions. We have time for maybe 1 or 2 questions from Zoom, if you want to ask.
Yeah, let's do one question because it's 11:05. The question reads, I'm wondering whether the robustness of the network matters in editing, because some papers find that for non-robust classifiers, the neurons may not capture semantically meaningful concepts, and they may capture high frequency noise.
Yeah, so when you look at even if the networks are not robust, generally when the input are natural images, they behave fine. So they are editable, and the unit seems to be quite reliably detecting concepts. So I don't think that's an issue there. I think that when you have robust models, depending also on how you made them robust, depending on the type of regularizations, sometimes you actually might make the network less interpretable. There are a number of techniques that you can use to regularize a network that will actually mix the concepts, and they will appear not interpretable. For instance, dropout is an example of something that if you do it in a layer, that layer loses interpretability. So I don't think that a technique that makes a model robust will make it necessarily more interpretable. It's going to depend on the technique. But in general, yeah, a model that works better generally is more interpretable. But I think that, because we are not dealing with adversarial attacks here, We haven't seen any behavior like that. However, one cool thing is that when you do adversarial attacks of networks, if you look at the units that get activated, you can see that the output is wrong because of the adversarial attack, but you can see also that the units inside, they believe they are detecting concepts that correlate with the actual output, so with the new false output, and so all of the units are full very early on. So if there is a unit that was detecting, if the final output, that thought that something was an office when in fact it was not, there will be internal units that will start seeing like computer screens and so on, even if there are none there. So they are susceptible to attacks, but they are still interpretable.
Okay, thank you. Oh, we have one more. Okay, last question.
I'm happy to
this
take
session.
questions also after.
Wondering in this final paper, like when you were doing the presentation masks, did you analyze if they respond to like single or multiple neurons in the communication? Like, are they clearly different angles or are there any interesting behaviors that we see for the analysis?
Yeah, here in these segmentations, they correspond to multiple units because generally one single unit is not selected to the whole class of objects. It's generally selective to, as this is why we use this open vocabulary annotations of units, because one unit might be selective for, I don't know, frontal views of cars or airplanes of a particular size. So you need multiple units to get invariance. So this is using multiple units.
Okay, let's thank the speaker. Yeah, thank you, Antonio. This was great. I really enjoyed it. Okay, so now we're going to have our first Zoom talk. So just for the people who are not there before, we have slight audio issues